streaming right now.
Okay. And then eventually you edit it? How it works?
So tomorrow I'll cut off this. Basically, I'll just trim the stuff before and after.
I see. And then, okay, good.
Yeah, because people care about this part.
Yeah, for sure, yeah.
And usually it'll be posted to the YouTube channel by tomorrow.
Okay, good. No, it's funny, Mike. Okay. Alan. טוב, טוב. כן. כן. טוב, זהו, אז זהו. אוקיי, ביי.
Is there an expectation if it does happen, how long it might take?
We're going around today talking to all the grad students and talking to all the faculty, trying to get people to move things up, all galloped prepared to just shut down the building. So hopefully if that happens, it'll be done after the first day. Fingers crossed.
You think it's you're thinking about one day?
Yeah, what?
You're thinking about one day?
We're hoping for at a maximum 2 days, but
Okay.
that's not. There's no guarantee of that.
Because I'm now thinking about two things. One, my classes, and another is just talk whether or not to postpone it by a week, or maybe move it to Thursday. And I'm now actually getting more inclined to move it to the next week.
Well, we could also see if there's a room.
Yeah, we can move it to a different room, but I don't know.
That's what I'm doing with my class.
They gave you for my class a room in a Mumford Hall, and I don't.
I asked 3 weeks ago.
I
was prepared.
I just know that they're going to give us a room in Mumford Hall.
Well, that's because the entire quad is being ticketed, so. And I don't think.
So I don't want to have a seminar that far away from from here.
But I know I'd like that very fast.
Yeah, the issue is that everyone's the issue too is that there's going to be people around screaming outside, so it's not going to be conducive to.
Right. Speaker today is Gerhard Hartmann from Northwestern University, and he's going to tell us something about which groups have bounded harmonic functions.
Okay, thank you very much first for the invitation to come to speak here. I want to tell you about a joint project with Josh Frisch, Omer Tammuz, and Puya Vahidi Ferdowsi about bounded harmonic functions. At the beginning, I'm going to tell you some stories, then related to results, and then I want also to show you some parts of our proof. Okay, so I'll start with the stories. So there are infinite groups out there, and we want to think of a notion of compactification or a good compactification for groups. One way to go is to take an infinite group and to add 1 point to have the 1-point compactification, but this is not very interesting examples. It doesn't tell us much about the group. And in fact, what I want to discuss is what is the class of groups which are too small to have any interesting compactification, but the trivial one. But for that, I need to explain what do I mean by good compactification, I guess. So let's start with classical setup where we have an object and we know its boundary and try to see what is going on here. So here I'm taking the complex plane, and inside I'm taking D is the open unit disk. Okay, we know that in this case the boundary is just the unit sphere, but how can we see it in another way, but staring at the picture? So it goes back to the Dirichlet that asked the problem. So given a body, you have a body, and there is a temperature on the boundary of the body, and Dirichlet asked to find the temperature at any given point inside the body. Okay, what is the property of this temperature function inside the body? It satisfies the mean value property, or it's harmonic. So any point, the temperature of a point is just the average of the temperature around it. So, and this is how harmonic functions are coming into the play. How, the solution to the Dirichlet problem is given by the Poisson transform. And it goes like this. So for every point inside the disk, inside here, I want essentially to find, no, wait. First, I take a function f. This is a function, a bounded function on the boundary. So this is the temperature. And you can think maybe as an example to have here 1 maybe, and on the rest I'll put the 0 temperature. And then at every given point x, what you can do, you can start to make a small perturbation of this point until it hits the boundary. And then you get, for any x, you can associate a probability measure on the boundary, which is the heating distribution for this point. So this point starts from here, and in this case of this boundary condition, it just asks what is the probability that this particle will end his process when he is lying in this part. Okay, and then what is the solution? How can we construct a harmonic function given these functions? So h of x would be now integrating the boundary function according to the distribution, to the heating distribution. Okay, but it gives us something very nice. The Poisson transform is actually unique. There is a unique solution, meaning that we got an identification between L infinity functions on the boundary and bounded harmonic functions on the interior of our object, which means that bounded harmonic functions, although they are defined on the object itself, they completely reveal the boundary structure, which is good. Now, before leaving the classical setup, let me recall the Liouville theorem that states that there are no bounded harmonic functions on the whole plane but the constant, which I want to think of as the whole plane has a very trivial boundary. There's only one point. Somehow you should think, or I want you to think, of the plane as being compactified with a single point. Okay. Now I want to discuss groups. So okay. So from now on, let gamma be a countable discrete group. So here I had a notion of harmonicity by saying I have a neighborhood of a point. Now in abstract discrete group I don't have such a notion, and for that I want to discuss measures on or if you wish, Laplacian on gamma. So and fix and let mu it will be a probability measure on gamma, which is generating. This will be a standout assumption. What do I mean by that? I mean that the support of mu, or at least if you take nth convolution of that and you union it, you get the whole group. So the support might be the support of the nth convolution. It means that as a semigroup, the support generates as a semigroup the whole group. Okay, now the basic definition: a function h from gamma to r is mu harmonic if the value at each point is the average of the values around it, where around is according to this measure. Okay, so by that I get a collection. So I'll denote by h infinity gamma mu, all mu bounded harmonic function, bounded mu harmonic functions. And you can study this object. What are the bounded harmonic functions in the group? Now, just as in the classical setup, there is a boundary that hiding here. This is a theorem by Furstenberg. Given gamma and this pair, a random walk in the group, there exists a probability gamma space that we call denote by pi of gamma mu. We call it the Furstenberg Poisson boundary. Such that, just as here, bounded harmonic functions on the boundary are in one-to-one correspondence with temperature values on the boundary are in one-to-one correspondence with bounded harmonic functions on my group. Okay, and just as the Poisson transform, also in this case there is this identification is coming through a stochastic process, which is a random walk or the mu random walk on gamma. And it's the following process. I'll just mention it briefly. So you take a lot of elements, GI, they're all distributed according to mu. You pick a lot of independently IID mu elements. And then you think of the process where the random walk at the beginning stands at the origin at E, and then goes to G1, and then goes to the multiplication of G1 and G2, and you keep on going like that. And you walk around. And as an example, let's take the free group. And although I said that it's a probability space, you can think of this space as being attached to the group, like that. And you can also think the probability measure, nu here, is the heating distribution. Okay, there is a way to associate the random walk starts here and it goes around. And there is a way to define what is the heating distribution on the boundary. Moreover, as we did here, we want maybe to start the element, we want the element not to start from the identity, but somewhere else. So you can define it really, we can think of nu sub g, this is actually will be g nu, are the heating distributions on the boundary. So these are different measures on the boundary, given that you start from the little g. Okay, so for example, if you think of a temperature condition here, before that. Okay, and then the Poisson transform, or this identification, is given by from a function in L infinity of the Poisson boundary. You can construct the harmonic function, which is given by h of g to be the integration of f, well, let me do even b, d g nu or nu sub g of b. Okay, so it's really a generalization of the classical setup, and here's the following Liouville theorem. We defined mu, probability measure on gamma, is said to be Liouville if the only bounded harmonic functions are constants, or it will be easier to me to think of it as the boundary being trivial. There is only one point. A corresponding compactification is a one-point compactification. Okay, let's do some examples. So the first one is a simple random walk on Z. So I have mu of 1 equals mu of -1. So it is this known process of this guy that drank too much. And he's going to the right and to the left with equal probabilities, walking around. Okay, what does it mean that a function is harmonic? Function on Z is harmonic with respect to this measure. It means that you have a value, but the value at any point is the average of the neighborhood, the neighbors. So harmonic functions here are just arithmetic progressions. And the only arithmetic progression which is bounded are the constant. So here you get that no bounded harmonic functions. Okay, now you might say, okay, it's a cheating because the random walk here is recurrent, so the guy will come back again and again, so of course you won't see anything interesting in the boundary. But even if you change the z here to z cubed, for which and you do a 1/6 to each direction, the random walk will be transient, so you will come back only finitely many times to the region. but still you won't find any harmonic function, then it corresponds to the fact that somehow, although it is going to infinity, it won't stick to a certain direction. The random walk will go something like that, and it won't stick to a certain direction. Or in other words, if you start the random walk from the origin or from any other point, after a long time, you won't be able to distinguish between the distribution of these two processes. So at infinity, you see nothing interesting. Okay, luckily there are groups with bounded harmonic functions, and it's written actually on the board. So, so I want to say simple random walk. So simple random walk on the free group. So this is the probability. This is the measure mu of A equals to mu of A inverse mu of B inverse equals 1/4. And so it is really the same simple random walk. At each step you go, you pick randomly 1/4 of one of the fourth neighbors. And here you do get bounded harmonic functions. Again, you can think of the temperature here as being 1 and the temperature here as being 0. And then you ask yourself, okay, at any point in any element, group element in the free group, what is the probability that he will end up in this branch, in the right branch? This will give you a non-constant bounded harmonic function, because the probability to hit this one would be, I guess, 1/4. But if you take a point which is so close to the boundary here, the probability will tend to 1. Okay, so the question that I want to ask is written here actually. Which groups have bounded harmonic functions? Okay. So, any questions so far? I guess that this was the story part. And now we're... Right, so here, exactly. Right, so this is the first is due to Furstenberg. That for non-amenable gamma, the Poisson boundary is never trivial. For all generating as usual mu. Then he asks, what about the other direction, or something that is known as the Furstenberg conjecture? At some point, it was proven by Kajmanovic-Vershik in 83, and Rosenblatt in 81, that the converse is also true. So any amenable gamma has a measure, a generating mu with non-trivial Poisson boundary.
Remind us of what amenable means again, please.
What?
Remind us of what the amenable.
Right, yeah, so amenable, and this is exactly how they did it. Amenable here, okay, there are a bunch of definitions, I guess, but amenable here would be that there is a sequence of probability measures on gamma which are asymptotically invariant. So it's a sequence of probability measures which that become more and more invariant. And this is exactly the task in proving this result, is to take these measures which are all over the place and to construct a single measure whose own convolution will become more and more invariant. Because this is exactly what is needed here. Okay, so this is the one side of the question when you have some measure. The other question is the following.
known for quantum groups?
There is some study, but I don't know. I don't know what is known. Right, right. So I should ask him. So the question is that I want to ask is which groups have trivial Poisson boundary that are too small. Okay, the trivial Poisson boundary for all generating mu. So they are too small. This is what I said at the beginning. They are too small to have to exhibit any boundary, interesting boundary, and these called a Choquet-Denis. Choquet-Denis groups, and this is due to the following theorem by Choquet-Denis. In 60 and Blackwell in 55, abelian groups are Choquet-Denis. Okay, so this is much stronger than what I told you here. It's not only Z or Z squared, it's any abelian group. Doesn't matter if it's finitely generated, not finitely generated. What about the measure? Any measure, it's very algebraic.
Is there a connection to extreme amenable groups, or there's this extreme amenability? Have you heard about this? Which is also such a super strong weird property, which is stronger than amenability.
Extreme amenability. So I know about strong amenability.
Extreme, yeah.
But not about extreme.
Well, there's this could be. I mean, there's essentially every representation is a fixed point or something like this. Bluntly, every without any extra conditions, even continuous or so. But I think that's.
Okay, so
that's what I heard, but it sounds something.
Okay, luckily we have the other direction, and this is what I want to present. So for this question, it won't be this one, but
okay.
yeah.
Can I ask a
Yeah,
question?
sure.
So in the theorem of Kimorovich and so on, do we know anything about that measure? Like, if our group is finitely generated, can we make it have finite support?
So definitely not.
Okay.
This measure can be chosen to be symmetric, but it might be crazy measure. So there are examples. If you did Lamplighter on Z cubed, for example, you won't be able to find any finitely supported symmetric measure with trivial boundaries. So sometimes you need to go crazy to find these measures. This is kind of an abstract.
So I'm more confused about the other sort of example. So which is what's the simplest example of an amenable group which is not Choquet-Denis, so where the Poisson boundary is non-trivial.
So I think that I'll get to it very, very soon. Here I'm only in the 60s, right? We have a long way. But okay, the next step is to do it inductively. This is Denking and Malyutov in 61, and then a very elegant argument by Margulis. Margulis from 66 says that not only abelian but nilpotent groups are Choquet-Denis, and I left a space here because you can do virtually. Doesn't really matter. Finite index doesn't matter here. Okay, but more or less since then, it wasn't clear what is the precise class of groups with this property. Maybe I should say, and this is exactly the time, that the difference maybe I should have asked you, what is the difference between these two examples? Okay, so one difference is here that you see that the growth is polynomial, but here it's exponential. But I want to claim that this is not the main issue. I want to claim that it's the fact that this is very abelian and this is very non-abelian. So the commutativity, I want to claim that the commutativity is the thing that plays the role. Just as an indication, here you don't even need the group to be finitely generated. The abelian or nilpotency or virtually nilpotency, these are so soft argument, these are not even about the growth. I know that nowadays when we see virtually nilpotent, we say, okay, it's polynomial growth, but it's not due to that, and of course it's before Gromov's theorem. Okay. So then in 83, in this Kamenovich-Vershik paper, they also introduced the entropy theory to discuss the reality of the boundary, and they show that that finitely supported measures on sub-exponential growth, they will have trivial boundary because there are not enough room to create entropy. But it only works for finitely supported measures, and then they conjecture, Kamenovich-Vershik, they conjecture that groups with or of exponential growth are not Shokedeni, and they ask it for non-finitely supported because there exactly they discussed the example of the Lamplighter. So they knew that it cannot be solved using finitely supported measures. So this was conjectured in 83, and then the main progress was where? Due to Anna Elschler, in 2004, where she showed two things. So for finitely generated groups, for finitely generated solvable groups, virtually nilpotent is equivalent to Shokedeni. And she found examples. There are sub-exponential growth groups with non-trivial boundaries, so which are not Shokedeni. Okay, and so this was what's known, and our contribution is to give the other side here. So this is again with Josh Frisch, Omer Tammuz. Oh, maybe my name here. And Puya Vahidi. Ferdowsi. So for any finitely generated group which is not, okay, for let me put it that way, for finitely generated groups virtually nilpotent is equivalent to Shokedeni property. And in fact, we are not talking about only finitely generated groups, but any countable discrete groups, also if it is not finitely generated. So I'll mention it in a minute, and this is exactly where I want to make the claim that it is not about the growth, but about the commutativity. Okay? Okay, so now I want to give you some indications of the proof, how the proof goes here. Okay, so the main question is, I'm giving you a group which is not virtually nilpotent. What kind of property? Oh, I mean, what do you get? What do you know by that? Right. Okay, so here's the definition. A group has the infinite conjugacy class property so ICC if any non-trivial element has infinite conjugacy class. Okay, so these are the ICC groups. And yeah, maybe let me say that this is the strong negation of abelian that I meant. So in a abelian group, any element has very finite conjugacy class. It's a singleton. The next step is to consider elements in the group which has finitely conjugacy class, but then it means that they commute with a finite index subgroup. The centralizer is a finite index. So up to a finite index, they are again kind of abelian. And these elements, or elements with infinite conjugacy class, they are really strong negations of a commutativity. Now, there is something here that I'm hiding. You can think, okay, you can take any group and take all the elements of finite conjugacy class. This form a normal subgroup. You can mod out by this normal subgroup, but you don't left out with an ICC because there might be element that at the beginning they had infinite conjugacy class, but after modding out by they get only the conjugacy class becomes finite. So there is something more sophisticated that should be done here, but this is the main property, and it's a theorem by McLean from 56. So a long time, even before I was born. That states that a finitely generated group is virtually nilpotent if and only if, or let me say that it is not virtually nilpotent if and only if it has an ICC quotient. So you can mod out by something and then you get an ICC. And this is really what we're using. And this is why we don't really talking about finitely generated. I just put it here in that way, but this is not what we think. Okay, now here's an observation. If you have a quotient, if gamma has a quotient which is not a Choquet-Denis, so it has their bounded harmonic functions, you can pull back the story to conclude that gamma is not Choquet-Denis. So the task is to work with ICC. So this is the property. Now I have an ICC, either finitely generated, maybe not finitely generated. Cook up a measure mu with non-trivial boundary. Yeah. Okay. So, yeah, so what I want to say is the proposition by proposition that given an ICC group, there exists a generating measure with non-trivial boundary. And this is what I want to indicate the proof. How can you use the ICC property? But before that, how can you tell that that a certain measure has bounded harmonic functions or not? So this is a well-known claim in this field that you want to think of random walks. So if mu of E is positive, so this is called lazy random walk. Sometimes the random walk just stays where it is located, and there is some H element in the group such that the lim inf of the total variation norm between H mu to the n and mu to the n is positive, then there are constant, okay, there are non-constant bounded harmonic functions. It should not be a surprise because, right, this is the random walk that starts from the region, this is starting from somewhere else, and if you can tell them apart, eventually, so you get a non-trivial boundary. Okay, so what do we want to do? I want to exactly, yeah?
The one.
This is the total variation. So it is exactly the opposite of what Kamenovich-Vereshik did, in Rosenblatt. If they took measures and cooked up a single measure whose convolution power becomes more and more invariant, we want to cook up a measure which are less and less invariant. Okay, it would be great if you can make the support of this one and this one to be disjoint, right? This would be fantastic, but we cannot. Okay, it's a bit too optimistic, but after you throw a small probability set, this is exactly what we're going to get. And here I want to say how to indicate some simplified version of the proof. So now I have an ICC, not necessarily finely generated. I'm going to construct the measure in the following way. Let me take a look in there. Okay. I'm going to construct a measure in the following way. We'll take P, some probability measure, on the natural numbers that I'll say later what exact probability do I want. And then we list G1, G2, like that, elements in gamma. And eventually the measure mu will give to Gm the P of the natural number m. Okay? Makes sense? So now I only need to tell you two things. Is what is the measure P on the natural and how to list the okay. So first I want to list the element. But for that, choose your favorite H. First, let H be fixed. Okay, not E, be fixed. And then we're going to make this element to act non-trivially on the Poisson boundary. Yeah. So I'm going to list this element by induction. So So say that, yeah, sure.
This is a fact about a single measure, right?
Right.
Is this an if and only if?
For mu of e, you mean if this is 0?
Mu of e is positive.
Yeah.
If there is an h, okay, then the harmonic functions are non-trivial.
So if you want to say that any...
No. If the harmonic functions are not trivial, or if they are trivial, then this converges to 0 or something like that?
Yeah, it will be, if this is 0, so you'll get that it converges to 0 for any h.
So this is an if and only if.
Yeah, under the lazy, yeah.
Okay.
Yeah.
Because that's independent of the CE kind of problem, right? I mean, this is for one measure. If you
This
have
is
a
for
measure,
right.
if you have a measure,
Single measure, this is how you, yeah.
how you understand it. Good.
Yeah. Okay, so say that we picked already that we have G1 up to Gm minus 1. And then I want to consider the following set. So let B.
What's the basic induction? What's G1? Is it H?
No, it will be actually E. But
Okay.
yeah, so yeah, there's no base. You can start from. No, you can choose it to be E. Actually, it's a bit simplified version in the beginning. In the actual proof, I want to choose a long prefix of E. So it will be very lazy random. But fine. So I want to denote by Bm minus 1 the following set. So it will be H and G1 to the plus or minus 1, G2 up to Gm minus 1. So all what I already chose, okay, plus or minus, and add also H there. And then I want to choose choose Gm such that, so I want to think of this set, Bm minus 1, and maybe to raise it to some power, maybe 4m minus 1. Okay, so take words of some length of this, and I want that the conjugation by this little Gm, I want it to take it very far from this set. Okay, so I want the intersection to be trivial. Okay, I cannot do it all the way empty, but I want it to be to meet only at the trivial element. Okay, so what is, these are huge finite sets, but I am ICC, so you can guess that you can take a single one that takes all of these outside for the other ball. I'll actually want, this is one property. The second property that I want Gm not to belong to this set. And that's all. The existence of these elements is guaranteed by the ICC property. And then I claim that this is the construction. Okay, so let's see why did I do that. So take now two sequences. Let S1 up to Sm and T1 up to Tm be a sequence of natural numbers. I want these sequences to have the property. This is, think of long. No, sorry. Here I want to do n. And say that the maximum of the SIs is the same as the maximum of the TIs is a number m, which is strictly larger than n. So I have 100 elements. The maximal number, 100 numbers. The maximal one is at least 101. Okay. So this sequence of numbers, they correspond to element in the group. So I claim that H and then GS1 up to GSN is different than GT1 up to GTN. So if you think of this sequence of numbers as the elements in the group, H takes this, these are really not the same elements. Why is it so? Because somewhere here, GM is hiding, and also here. So let's call this bunch of elements B1, and this one B2. This is C1, and this is C2. So what do we get? That if there is an equality here, so I want to move things around, so I get that HB1 GM C1 inverse GM inverse equals to C2 B2 inverse. But what are the B1, B2, C1, and C2? These are elements from exactly this set. Because GM is the maximal, so all the indices that you see here are strictly smaller than GM, and the length of the string is less than n, which is less than m, so we are in this setup. So that's all. You get a contradiction. Okay, it's not all the way because you get induction here, because it means that this should be something here should be the identity, and then you trim your string and it becomes shorter and shorter. But this is one idea. The other thing is that if GM appears only in one of them, it's even better because it means that GM belongs to this set. Okay. Yeah, so the only thing that now we need to do is to find this P such that these kind of sequences will become typical. So you want to find a distribution on the natural such that if you take a long list of samples with very high probability, you'll see a unique maximum, and this maximum will be larger than the number of samples that you took. And there are such things. These are heavy-tailed distributions. So you can take P to be distributed according to n to the minus. We took 5/4, but just some alpha where alpha is between 1 and 2. So these are kind of measures. They have a heavy tail. They don't have first moment. But this is exactly why you expect to get so huge numbers. So the numbers that you'll get will be larger than the amount of samples. And the probability that you'll get twice the maximal one tends to, it's very small as you take very long sequences. Okay, in the last minute, I'll say that what I showed you here is very nice, but this measure is not generating, and it's not symmetric. So you add some more layers here, and we did it for so the measure that we construct here, the measure here. That's a funny statement. Non-trivial. The measure that we construct here is a symmetric measure, a generating measure, not finitely supported, of course, and with finite entropy. So it's kind of, the finite entropy comes from, basically, you can see it from here. Okay, thank you very much. Okay, so it suggests, right? Yeah, maybe I should say a few words here. ICC, you can see, and also actually by the works of Kennedy, Kalanta, and then with Ozawa and Bouillard, what I said about Kajmanovic-Vershik, you can think of it. Okay, I don't want to get into much details. I can tell you later, but this whole project started by my three co-authors, where they proved that a group is ICC if and only if it is not strongly amenable. So strongly amenable is, and there it's very related to the von Neumann, to the group from Neumann algebra, and in some sense the amenability is the one that corresponds to the C-star, to reduce C-star algebra, and this somehow we get a nice picture.
So this Kajmanovic-Vershik stuff, you know, from the 1980s paper or whatever, did they have some condition, sufficient condition in terms of the entropy, which implies that the Poisson boundary is trivial?
Yeah. So if the random walk entropy is trivial, if the random walk entropy is zero, so then the boundary is trivial.
Oh, and that's what they used to do.
And now it follows that if your group is of
So
sub-exponential,
that was it, right?
Yeah.
I see. Okay.
sub-exponential growth with finitely supported, but yeah,
So it's a Google test.
exactly.
I see.
So here you were looking for bounded harmonic functions. What about
Positive.
integral harmonic? I mean, there's a measure you could talk about integral harmonic functions.
Right.
And what do you know there?
I don't know. Okay, I don't know. Somehow I'm coming from the random walk theory,
Yeah.
and I was after this question for a long time. But
Oh, it's beautiful.
yeah, you know, that's a good. Now it opens a yeah.
Okay.
It actually suggests also this correspondence about things in the strong amenability.
Yeah, so maybe there's
There's something that
something
more yeah suggests some statements there.
All right. Thank you very much again. All right. So for those who are interested, we'll reconvene by the mail room in a few minutes and go to Mandarin Walk.
I'd be glad to walk a little more slowly.
Okay.
What?
if you know this harmonic measure is a music down.